I am Professor Anis Vora and I welcome you all in this video lecture. In this video lecture, we will study about the different types of transistor, and that is a field effect transistor. We call it FET for field effect transistor, and FET is a semiconductor device in which control of current is done by electric field, and the conduction of current is possible only due to majority charge carriers, and that is why FET is known as a unipolar device, because only single polarity charge carriers are responsible for conduction of current, and the input resistance is very high. That is why it does not load the source. Now let us see the classification of field effect transistor. FET, that is broadly classified into two categories. One is a junction field effect transistor, and another one that is a MOSFET, or it is known as IGFET, that is insulated gate field effect transistor, or MOSFET, that is a metal oxide semiconductor field effect transistor. Junction field effect transistor is normally having two categories, that is N channel and P channel, while MOSFET is again divided into two categories. One is a depletion mode and another that is enhancement mode. Junction field effect transistor, that is normally in the depletion mode only, and in case of MOSFET, depletion mode and enhancement mode, both the modes are again classified into two different categories, that is a P channel and N channel in both the mode. So this is entire summary of the classification of field effect transistor. In this video lecture, we will start to study about junction field effect transistor, but normally we call it field effect transistor or FET. In case of a junction field effect transistor, we have two categories. One is N channel and one is P channel. In this video lecture, we will study about N channel junction field effect transistor. Let us start with the construction of N channel field effect transistor. We have N type of channel. So N type of semiconductor material lightly doped is taken, and that is known as a channel. Two terminals are taken from the N channel, and that is known as a source and drain. Drain is a D, capital D, and source we denote by capital S. It is like a collector and emitter in bipolar junction transistor. Then we have P type of semiconductor material heavily doped on both the side of the N channel, and it is known as a gate. We provide voltage across the drain and source, and that is known as a VDS, so voltage across drain and source. And in N channel, the drain is supplied with positive polarity and source is grounded. And same way, we apply voltage VGS, that is across gate and source, and gate is a P type of semiconductor material, so we reverse bias our gate. So VGS, that is voltage across gate and source, that is applied between gate and source, and gate is reversed biased by applying negative polarity voltage. Now let us see the physical construction of the N-channel type of field effect transistor. We have taken N type of semiconductor which is lightly doped, and it is known as a channel. On both the side of the N type of semiconductor material, we have P type of semiconductor material, and that is a heavily doped. And then 3 terminals are taken out, and that is known as a gate. From the P type of semiconductor material, we take a gate from both the side. Then from the N channel, we have taken source as well as we have taken drain. And this is known as silicon dioxide. A layer of silicon dioxide is deposited. Let us see the symbol for N-channel field effect transistor. We have 3 terminals: drain, source and gate. That is like a collector, emitter and base in BJT. We can see the arrow on the gate, that is inside, and that is for the N channel. For P channel, the arrow on the gate will be towards outside. We have another symbol equally we use for a N channel field effect transistor. We have understanding of the terminals. Source. The source S is the terminal through which the majority carriers, in this condition we have electrons, enter the bar. And the current, conventional current passing through the source, that is denoted by IS, suffix S we use for source. Then drain. The drain D is the terminal through which the majority carriers leave the bar. In this condition we have N channel, so majority carrier is electrons. Flow of electron, that is from source to drain, and flow of conventional current, that is from drain to source, and the current passing through the drain is denoted with ID. We apply voltage, and that is known as a drain supply voltage, that is between drain and source. That is why it is known as a VDS, and that is actually VDD. Normally we write VDD, that is drain supply voltage, but the application of drain supply voltage, that is across drain and source. And gate. On both the sides of the N-type bar, heavily doped P region have been formed. P plus, that is heavily doped, and that is called gate. And the current passing through the gate, that is denoted with IG, G suffix for gate. And the voltage we applied across the gate, that is a VGS, that is a across gate and source, but normally we call it gate voltage VGG, and that is minus because we reverse bias the gate. Channel. The region of N-type material between 2 gate region is the channel through which the majority carrier move from source to drain. In N channel it is electrons. Now let us see the working. We have N channel, and on both the side of the N channel we have P type of semiconductor material which is heavily doped. We supply drain voltage, that is with the positive polarity, to the drain, and conventional current pass from drain to source. Because being a N channel, the majority carrier, that is electrons, So electron pass through source to drain, and the supply voltage, that is a drain supply voltage, and it is known as a VDD. And the current passing through the drain, that is our conventional current, and that is known as a ID. But when we reverse bias the gate, that is a P type of a substance and it is a heavily doped, we apply voltage VGG across gate and source, and we reverse bias the gate. So in the absence of gate voltage, drain current pass through the channel by majority charge carrier, but when we apply gate voltage across gate and source, and when we reverse bias our PN junction, there is a depletion layer is formed in the channel, and the depth of the depletion layer, that is more in channel because it is lightly doped, and in P type of substance it is because of a heavily doped, the depth of the depletion region is very less. So when we apply a reverse biased voltage across gate and source, a depletion layer is formed in the channel, and that is known as a depletion region. There is no charge carrier in the depletion region, and that is why the region will act as an insulator. So as we go on increasing the gate voltage in a reversed bias condition, the depth of depletion region goes on increasing, and as a result, the drain current of the majority carrier will start reducing. As we apply more voltage to the gate in a reversed bias condition, then the depletion region join together and drain current becomes zero. So this is how, with the help of gate voltage, we can create a field effect, and we can control the current through the channel, and that is why the name is given as a field effect transistor. Thank you very much for watching my video. Keep watching. Thank you very much.